Thank you very much for having me here. I'm very happy to be amongst all of you to share my thoughts on this topic, rural connectivity. So, right. So this is my talk outline what I've planned is I'll try to motivate this topic from a very general perspective, like what is going on in the networks community uh, and what are the uh, what are the advances that have been coming up to provide rural connectivity. Okay. And then we'll talk about the our work that we are doing at IIT Ropar. Okay, so the introduction is, as you all know, the almost half of the population lives in the villages worldwide. Okay, and so more so in India, right? So we have a lot of small villages, and right, and majority of the population lives in villages and towns. Okay. Now you see, the statistics goes like this, that almost half of them are unconnected. Okay. So almost this statistics is a old one, but the scenario remains pretty much the same. So it's like 3.9 billion unconnected people in 2018, whereas it was 4.4 in 2014. So 75% of these unconnected people live in rural areas with those people having low income and low literacy rates. Right? And amongst these population, unconnected people, 85% is from the developing countries. Okay, so almost 50%, 15% is from the developed countries, and Asia and Africa contribute the most. Today, I just was going through the Hindu paper, and there was a nice article which says there was a recent survey that was conducted by Oxfam, and it said that 16 crore more people were forced into poverty due to the pandemic that we are undergoing. So we are seeing that a lot of people are these poor people. They are actually not getting connected to the internet facilities, to the broadband facilities. So this is what I'm trying to make. And so there is a huge digital divide between the rural and the urban area. Okay. So you see that because majority of the population in the rural areas, they are not connected to the internet. So there is a big digital divide. And I'll talk about what do I mean by digital divide. The internet penetration depends upon the per capita income. Okay. So if at a particular location the people are rich, they can support these broadband facilities, and therefore the internet reach to them is pretty easy. Okay. So we can easily see that in the urban areas where these are economically strong, people are wealthy there, we can see that the internet penetration is huge there. Okay. But if we move towards the rural areas where the people are poor, they cannot afford expensive services. So we can see that the internet penetration has gone down. Okay. And the studies suggest that if there is a 10% increase in broadband connectivity, broadband penetration, that actually leads to or contributes to 1 to 2% increase in the GDP. So you can see that there is a huge contribution of this broadband facility or the internet facility on the GDP. Okay. And obviously with this this IT infrastructure, this internet infrastructure, people can do a lot of things, as we have learned during the pandemic. Higher local employment, we can see that a lot of people are working from homes, and many of our students are actually taking classes online. So if we do not have a better internet facilities in these rural areas, then we can see how the people grow there. Okay. So the overall social well-being of those people suffer because of this internet connectivity, and therefore the employment rates, the number of businesses that we create, and so on. So there is a direct link between the internet penetration and the socio-economic standard of living for the people. Okay. And this same idea has been attracting the attention of World Bank, the ITU, and the Indian government also is putting a lot of emphasis on providing rural connectivity. So what is the main difference between the connected and the unconnected, or you can see the urban and the rural populace? Is one thing is the affordability and low income, because we have low per capita income in the rural areas, so therefore they cannot afford higher expensive services. Incentives are also less because there are only few people who are literate, who can work on the internet and then figure out things. They can make use of the internet in a best possible way. Okay. Then the infrastructure also plays a critical role. To work on the internet, you again require electricity and the other facilities also. To set up those infrastructure, you again require a proper transportation mechanism, for example, nice roads. Okay. Then certain more facilities, water, electricity, these are the basic facilities. So these are lacking in these some of the remote rural areas, and therefore it is difficult to get proper infrastructure to these places. And again, diverse terrain is another big challenge. We see our Indian subcontinent, it has all kind of terrains, vast desert area, the mountains, the valleys, and so on. So we can see these diverse terrain also create a lot of problems in setting up a proper infrastructure. So again, so why we are not having a proper network deployment in these rural areas? Again, the first thing is because of the lack of business due to sparse population, as well as the population which cannot afford such expensive services. Now, if you look from the business perspective, how these operators work is that they put up some towers which requires to put some capital expenditure is there to establish this base station towers or infrastructure, the backhaul facilities, and so on. But the number of users that are using this service is pretty low, because if you see in the rural areas, there are the village population is sparse. Okay. So some people here, some people there, and so on. So you cannot have just one base station connecting to all the users. You need to have separate base station for each village, and so on. So again, this high capex cost comes into play. Then again, OPEX cost, operational expenditure, also comes into play. For example, electricity, if there is no electricity, then you have to arrange for a generator. Then again, fuel for the generator, for example, diesel, and so on. Then you need to have skilled maintenance, skilled manpower to operate all those equipments. So you can see that a lot of expenditure is required to establish these networking infrastructures in the rural areas, and therefore these companies do not get that much return on the investment that they have made. So therefore they are not motivated enough to establish such networks in these areas. But from a humanitarian perspective, we could see that now network has become almost one of the necessities, and this IT infrastructure is contributing a lot in terms of health, in terms of education, in terms of creating businesses, in terms of providing jobs to the people, and so on. Okay. So from humanitarian vision, from the humanitarian perspective, we must provide equal broadband facilities to all kind of people. Okay. And that is the people are pushing toward this as a fundamental right of the people. Okay. So therefore, this government comes into picture, and they want to develop such kind of networks which can provide equitable facilities to all. Now we all have been hearing about 5G for some time now. The basic three main points of the 5G is enhanced mobile broadband, massive machine type communications, and URLLC. But you can see that 5G does not cater to the rural community, because again it is more focused on providing services in a small cell. You have millimeter wave communications, and then you have high data rate communications. Okay, so it is more suitable again for the urban perspective, where you have more data demands, not for a rural, from a rural perspective. So in 6G, what we are actually envisioning is something which is contributed towards the rural connectivity. This is what we are envisioning. So we want to move from 5G engineering to 6G humanity. We want to see from a humanitarian perspective, not from a commercial perspective where everything is in terms of money. So service must be affordable and sufficient for all the people. Okay. And it just not just the technical problems, but also the regulatory and operational issues also needs to be overcome to provide rural connectivity. And there needs to be some regulations that have to be developed towards this end. Again, without getting the commercial players on board, it would be very difficult to have rural broadband connectivity. So it is very much essential that the stakeholders cooperate and then come up with a better solution to provide broadband connectivity. Okay, what are the typical applications that we see in the rural community? Education, as we all know, because of this pandemic thing, everything is now getting online. Even after this also, after the pandemic gets over, I think most of the things would be online. For example, these kind of lecture series. We did had online courses, but now that will be even more pronounced, and so on. Health, again, telemedicine, e-consultation, e-diagnosis. Farming, in rural community mostly depends on agriculture. So if we can improve their agriculture experience, we can improve the productivity using the IT infrastructure. That would be very nice for them. Precision agriculture is what is being focused on currently. Drip irrigation, cattle tracking, detecting diseases in the plant, how the plants are growing, okay, and so on. So, and a lot of technologies are being developed in this direction, for example, using UAVs and drones. And to back up that, we have a lot of other protocols and technologies coming up like LoRa, MQTT, and so on. Okay, business and financial services, we can have more ATM facilities or POS or facilities, so that people don't need to travel to the nearby towns for banking facilities or for connecting over the internet, right? We now see that all the financial services are now accompanied by OTPs. So if you do not have a proper IT infrastructure, then these all services, they go down, right? And then there could be other applications also. For example, we now buy all tickets online. We don't have to stand in a queue. So we all want all these facilities again for all the people in general, not just for the rich people or people from the urban areas who can support these kind of facilities. Okay. In the rural areas, we also want surveillance of the railway grid, highways, power pipelines, power lines, and so on. And e-governance is again a very big thing. We see most of the schemes that the government comes up with is for the rural community. And if there is no proper communication, then how the people living in these rural areas will get to know about these schemes. So we can see a plethora of applications that we can have, a plethora of services that we can have for the rural community once this IT infrastructure is strengthened. Okay, I'll briefly talk about the technologies what have been developed for this particular scenario. From the 5G networks perspective, we could see that it was primarily built for the urban context. So these were basically what they said is that we want to increase the capacity of the cell, or we want to increase the data rate. So make the cells small enough and use high bandwidth spectrum. That's what was that is proposed in 5G. There is a group in IIT Bombay which worked on using this 5G to provide services in the rural areas. So what they said is that we can have Wi-Fi access point in the villages. Users can connect through Wi-Fi, okay, in the villages, and the mid hall could be a multi-hop fiber optic cable. Okay, so this was they proposed. Again, so this is the proposals. I'm just going through some of the proposals that people have given for rural connectivity. I'll talk about some of the our takes on these proposals, and then I'll talk about what we contributed to in this direction. Okay. Again, UAVs can be used to provide connectivity in these areas. For example, you can have a UAV base station which can hover over a village and then provide connectivity. So in this way, you don't need to have a fixed infrastructure. You can have just a UAV which just flies over there, provides connectivity for certain time and then come back. Again, you can understand that the service will be intermittent. Okay. Direct satellite access is another communication facility that people can have, but again, it is costly and there is a lot of delay involved when we are connecting to the satellite. Recently, there has been a lot of news on these LEO satellites, for example, Starlink, OneWeb, CubeSats, and so on. So they are actually deploying these satellites on a LEO orbit, so which is like 500 kilometers, roughly 500 kilometers. So we can reduce the delay in our communication, but at the same time, we understand that we need to have a lot of satellites to cover all across the globe. Okay, so almost 2,500 satellites are required to cover the entire globe. And again, these LEO satellites actually they are moving, so they are not geostationary, so they are moving. So we need to handle the handover issues, and again how the data is to be routed, that needs to be seen. Another solutions that people have proposed is using Wi-Fi, WiMax, or multi-hop networks. You can have WiMax. WiMax is a point-to-point communication link. So you can have these WiMax towers at each of these different villages, and you can connect them through a multi-hop network. But again, you can see that we need to have some fixed infrastructure, which again creates the same bottleneck. Wi-Fi over TV white spaces, again, another good solution. People have also come up with standards on this particular solution using TV white spaces. So for these, I'll talk about this in more detail, the Wi-Fi over TV white spaces. Delay tolerant networks is another research direction that people have pursued. So what they say is that we can have, let's say, a data mule, maybe a vehicle which has the networking facility. It can go around the village, collect the data packets. It's like a postman. So it collects all the information, then it goes to the town, gets connected to the internet, again collects some data or gives out some data into the network, or collects some data from there, comes back to the village and then distributes. Okay, so it's kind of postman. So this is for a delay tolerant network, wherein you have applications which can tolerate some delays. Again, power line communications is another good area of research, because these power lines are there all across the country, so you can make use of these power line cables to carry your data information. But what we have seen is that it can carry a very small amount of data rates. There is a lot of noise involved in these power line communications. Okay, so from the TV white space perspective, we could see what are the TV white spaces is the TV bands. We uh, uh, let's say for before 5-6 years back, we had these analog TVs that we used to have in our houses. So these were actually operating on UHF bands, 100 to 400, 500 megahertz bands. So once these analog TV transmissions stopped, so everyone now moved to the digital TV transmissions, so which are carried out at um, some 10-12 gigahertz on those ranges. So these UHF bands, which were for analog TV transmissions, they got vacated. So now these are idle. So they could be used for our communication applications. Now, what are the challenges in what are the benefits of these UHF bands? The benefit is that because as you go to lower frequencies, you can reach to larger distances. So that is the one advantage. So if you put a base station, it can cover maybe 30, 40, 50 kilometers of area. So it can cover multiple villages, can be covered using a single base station. Now, what is the problem with this kind of a scheme? The problem is that as you go to lower frequencies, you need larger antenna size. Now for base station, it is okay. You can have larger antennas. You can have, so we do have big towers. So we can have a big tower, which can have a larger antenna to transmit these these UHF signals. Now, what about the reception? When you have a mobile device, the mobile device cannot be a big device with a big antenna, a larger antenna. So, so the downlink is okay. Base station can transmit to the users, but the uplink is a bottleneck. How the users transmit back to the base station is a bottleneck. Okay. Again, a lot of standards have been proposed in this direction, but again, they take into consideration that the receiver is so transmitter receiver is going on in a point-to-point fashion. Okay, it's not a broadcasting, but it's a point-to-point fashion, and so you have a dedicated receiver with the dedicated antenna, which is pointing directly to the base station for the transmissions. Okay. So this was about the front haul connectivity. For the back haul, again, we need to have certain technologies which can provide connectivity backhaul facilities to these base stations. And there we can have lot of technologies. For example, fiber optics, microwave links, or free space optical links, and so on. And nowadays people are exploring other options also. For example, high altitude platforms like drones, UAVs, satellites for backhauling. Okay. So once you have you have deployed a base station in a rural community, rural area, we also need to have some backhaul connectivity to that. Okay. So for that, these may be some of the options, but again, these are under development. Okay. For example, if you have a UAV which is providing a backhaul, then again the backhaul is intermittent, or we do not get that much of data rate. Okay, so all those are still a challenge which needs to be addressed. So in a nutshell, there is a huge scope of technological development in this area, specifically from the backhaul and from the mid haul or the end haul perspective. Okay. Energy requirements are again a critical issue. We do not want to establish the energy hungry base stations at each village. That is again going to increase our energy requirements and increase our cost, increase our operational expenditures. And whatever technologies have been proposed till now have not thought about mobility also. So mobility is one such area which has not been thought of much. For example, if you're moving on a highway, then how do you provide a high-speed broadband connectivity there? Okay. And obviously the regulatory, the spectrum and the economical aspects needs to be also seen. So from the Indian perspective, the government has done a lot in providing fiber optic connectivities to each of the gram panchayats. So there is a BharatNet program of the Indian government, which is laying out the fiber optic cables to each of those gram panchayats. And again, there have been a lot of solutions that have been proposed in this direction. For example, using TV wide spaces to provide middle mile solution, to provide a mid-haul facility, mid-haul communication, and using Wi-Fi access points for end users. Okay. There have been applications also that people have proposed. For example, Vivek Diksha for telemedicine and teleeducation, Shame for e-health, Parik for microfinance. Okay, so what is the future direction or how to move forward in this particular area? Is we need to put all these things together, the front hall and back hall, and make a common, make a unified communication mechanism, which can be used to provide full connectivity as well as it has a backward compatibility or coexistence with the existing cellular infrastructure. We don't want the users in the village to use a different device for in the villages and use a different devices at their at in the cities. Okay, so we need to have a common standard which can cater to both the scenarios. Okay, and our ultimate target is that we want to bridge this digital divide, and we want to bring communication for all. So in this direction, we started working in this particular area, the rural broadband access. So we tried to come up with another solution, which was based on collaborative communications. So let me talk about that. So let's look at this scenario. So in a village, in a rural area, we have multiple villages that may be separated apart, and each village has a different strength. Okay. Now, what the conventional broadband architectures, what the people have proposed till date is that you can have a point of presence, which is, let's say, a gram panchayat, where you have a fiber optic connectivity. So your backhaul problem is solved. So once we have the fiber optic connectivity to the point of presence, we call it point of presence. So wherein you have a fiber optic connectivity. Now, from here, you need to provide your communication to the different villages. Okay. Now, one way is that suppose if I'm operating at TV byte spaces, so then I put up these UHF antennas, which are working on, let's say, 802.11 AF. So these are now point-to-point links, so they connect directly to the point of presence. Okay. And for the local people, there could be a Wi-Fi access point, or you can have a local 4G server or 5G server that could be that could provide service to the local people there. Okay, so in a village, you can have one or multiple these UHF band nodes. Okay, so which are providing mid-haul facility between the point of presence and the village users. Okay. Now the problem with such kind of infrastructure is that again you have to put up these UHF band nodes. Okay, and then you have to monitor them, okay, whether they are functioning or not. You have to maintain them, whether the electricity is proper and not, and so on. Okay, so again, this is a operational expenditure for the service providers. So this was one of the challenge that we saw in this particular architecture. Okay. So what we actually thought is that we don't want any infrastructure set up by the service provider in the villages. So we want that this point of presence, this base station, can reach to all the users, and vice versa. All the users can reach to the point of presence without using any intermediate infrastructure. Okay. So we came up with another strategy where we said that why don't the users, so the main bottleneck was, as I discussed earlier, the main bottleneck is that the point of presence, they can talk to all these users, they can transmit to all these users, because it has a higher power transmitter, it is a higher, larger antenna, and so on. So it has all the facility. The point of presence has all the facility to reach to all the users. But the users don't have that facility. So users may be having small antennas or small transmit powers. So how they will reach back to the base station? So this was the problem that we wanted to solve. So one thing we realized, that there is something called as collaborative communication, okay, or distributed beamforming. So what we said is that let multiple users come together and transmit simultaneously to the base station. So if they simultaneously transmit to the base station, their signals would add up, and eventually the SNR will go high at the point of presence. Okay. Now, one simple analogy is, if you want to call a friend of yours who is quite far away on the other part of the field, if you speak alone, he may not be able to listen. But suppose if a few of your friends come together and shout in a synchronized manner, then he may hear it. Okay. So it's a simple strategy of adding up of the signals at the base station when all of these transmit at the same time. Okay. So here what we said is that, we wanted to make use of some of the devices that are already there in the individual houses. So everyone knows that we had these TV antennas, which were used to receive the TV signals, analog TV signals. So we said that we will make use of those antennas, those Yagi-Uda antennas. Okay, and so we can use those Yagi-Uda's antennas and use our device, which we called it as customer premise equipment, CPEs. So we can use this device to communicate with the base station. Okay, so these devices can receive directly from the base station, and for transmission we can collaborate with the other nearby CPEs or devices, and then we can collaboratively transmit to the base station. So this is the idea. And how the users can connect? Users can again connect through Wi-Fi. Okay, these CPEs can have a Wi-Fi access point, which is pretty cheap nowadays. We can have these Wi-Fi access points where the users connect, and then they can communicate. Okay, so this is how we wanted to solve the we wanted to eliminate this UHF band nodes, and wanted to bring in some devices which are used in the individual houses to provide connectivity to these village people. Now, a little bit about what is distributed beamforming and what we are trying to do here. So it is different from MIMO. Okay, it shares some similarity with the MIMO, but I'll talk about what are the similarities and what are the differences. So in cooperative communication, what we do is that multiple transmitters, okay, multiple transmitters transmit simultaneously the same information, same message, so that at the receiver, all these signals add up. Okay, so if the signals add up, so we know if the amplitudes add up, it gives the power multiplies. Okay, so with distributed beamforming and n number of antennas, n number of transmitters, sorry, each transmitter has a single antenna. For the time being, let's assume this. So for n transmitters, we can get a range increase of n-fold. Okay, so suppose if you are using 5 transmitters, we can have a 5x increase in the range, or we can have a n square fold increase in the data rate. Okay, or we can have a higher in energy efficiency, and so on. Okay, so the main thing is that if these signals, we can get these signals added up at the receiver, we can get gains in the multiplication factor. Okay, now what is the main challenge here? The main challenge is that, so as we all know, the wireless communication, it is characterized by fading, shadowing, and channel noise. Okay. So what does this do is that it actually, whatever signal you are transmitting, it changes the phase and it introduces delay into the signal. Okay. Because of the multipath, you will get a delayed signal, and you'll have a different phase at the receiver. Now, the main challenge here is to get all these signals added up at the receiver antenna. Okay. And obviously, when these different transmitters are transmitting, so they don't have an exact frequency that they are transmitting. Okay. Two oscillators cannot have an exact same frequency. Okay. So we need to also synchronize the frequencies also, so that they all are operating at exactly the same frequency. Okay. So there have been a lot of algorithms have been proposed to solve this problem. So one thing is the master-slave approach, where the transmitters act as slave, the receiver acts as master. Master sends out some beacon signals, and the receivers then align their transmitters to those beacon signals. Okay. And actually these people have shown that over a period of time, there is a feedback mechanism that goes on between the destination and the individual transmitters, and over a period of time we can see that these phases align up. But again, this takes a lot of time. The synchronization part takes a bit of time, and which actually introduces delay into our communication system. Okay. So coming back again, so I'll talk about, so we are working on basically taking another approach of implementing this distributed beamforming in low cost devices. So we're working on that. So coming back to our architecture. So for this particular architecture, now we want to develop an access strategy, how the users will communicate their information to the base station or to the point of presence. This is the question we want to now solve. So again, this kind of a architecture has not been discussed in the literature till date. So this was a kind of a novel thing for us also to have this kind of a setting. So we actually came up with two-tier contention mechanism. So in the first tier, what happens is that these CPs have to, so CPs have to first form a cluster among themselves. So I'll talk about the cluster formation algorithm also in subsequent slides. So suppose if the cluster is formed and CPs know, okay, let's say 4 or 5 CPs have come together, formed a cluster. Now they have to contend to get a channel from the base station and then transmit their information. So I'm just concerned about uplink as of now. Downlink is pretty simple because the base station can reach to the user, so it is pretty simple. So for the uplink mechanism, so first thing is that the CPs has to first decide among themselves who is going to transmit. Okay, who has a data packet and who is going to transmit. So they will first contend among themselves using a simple slotted aloha protocol. So CPE will say, okay, request to collaborate or request to send, and the other CPs in the cluster will say, okay, you are clear to send, and then they can come together, they can share the data among themselves. Now, once the data is shared, then one of the CPE will then decide, okay, at the base station, I have to now contend for a data channel. Now, how the contention mechanism goes on at the base station is, we have a common control channel. Now this common control channel is divided into frames, and each of the frames is divided into small slots, which are called as contention slots. Okay. So this cluster then will decide, okay, one of the slot it will choose from a frame, and then it will try to push its contention packet on that slot. Now, how this system is different from slotted aloha is, if you see slotted aloha, all the users know, okay, who who transmitted in the previous slot or who did not transmit in the previous slot, and so on. And based on that, they can make some decision. But here it is not so. Here the thing is that if one cluster is communicating to the base station, the other clusters may not be able to detect that. Why? Because these clusters are transmitting using distributed beamforming, and it is assumed that this signal is getting added up at the base station. It can add up other places also, but it may not add up to other places also. Okay, so the clusters may or may not hear from other clusters. Okay, so only the base station would be aware whether the packet was transmitted by the cluster or not. Okay. So this is the difference between the normal slotted ALOA and this particular case. So this cluster chooses one of the slots in the common control channel and transmits its contention information. And in over these green slots, the base station computes, okay, from whom all it got the contention requests, and then subsequently allocates the data channels for transmission. Okay, and once the data channel has been allocated, the cluster can again use those data channels to transmit its information. Okay. So this was the access mechanism that we developed for our architecture. Performance analysis was done using these two parameters. One was the uplink throughput, amount of uplink data that was successfully transmitted per unit time, and the uplink energy efficiency, amount of uplink data successfully transmitted per unit energy consumption. I will briefly go through the analysis part, just to briefly explain what we did. Okay, I'm not going into detail of this. First thing is we need to figure out what is the cluster outage probability. So once these clusters are communicating to the base station or using distributed beamforming, then what is the outage probability? So that was computed first. And then for these intra-cluster contention, where these different CPEs are contending among themselves to say who is going to win and who is going to transmit its data packet. So there we modeled a discrete time Markov chain. Okay, and then for the intra-cluster contention, when these different clusters are contending amongst themselves for a base station channel, then we designed again a Markov chain. Okay, where the first line, if you see, this is for the intra-cluster contention. So a particular cluster is in intra-cluster contention phase. And then once it wins the intra-cluster contention phase, that means one of the CP is ready to transmit its packet. Then it enters the inter-cluster contention phase. Now here the cluster will now contend among the other clusters and then win a particular data channel from the base station. And once it is successful in this phase, then it will move to the data transmission phase, wherein the packets could be transmitted over the allocated channel. Okay, so this was broadly the DTMC that we figured out. And then obviously it requires the other metrics also. For example, probability that a given cluster is successful among k successful clusters in a frame with V clusters contending. So we did all this analysis and figured out the throughput and the energy consumption. So obviously, because this is in terms of the discrete time Markov chains, the steady state probabilities of these discrete time Markov chains. So we cannot get a closed form expression, but we have to actually draw these Markov chains and then figure out their steady state probabilities and then suitably compute it to get these metrics. Okay, so so this was fine. So for this particular case, we then plotted the uplink throughput and uplink energy efficiency that we got, and we compared it with the conventional scheme that I showed you in the initial slides, wherein we had these UHF nodes that are deployed in each villages. So we could see that throughput is pretty much the same in both the cases, but in the energy efficiency part, actually we did pretty well. Reason being that when these nodes, these CPEs are transmitting collaboratively to the base station or to the point of presence, so it requires pretty much low amount of energy for transmission, and that is where we gain in terms of energy efficiency. And also one thing we noted here is that these throughput and energy efficiency depends on the cluster size. So if you have a smaller cluster size, small cluster size means the number of transmitters participating in distributed beam forming. If they are less, then the gains that you're going to get at the base station will be low. If you have more number of users, then though you get good gain at the base station, but the problem is that because there are a lot of CPEs involved in a cluster, so there will be a lot of requests of packet transmission, and it will have more collisions in terms of intra-cluster contention. Okay, so that was the main point that we figured out from here, and that actually impelled us to look for an optimal cluster size. Okay, so again, this is an integer programming problem. So we used heuristics to figure out what could be an optimal cluster size. And based on that cluster size, now we have to develop a distributed clustering algorithm to form cluster of these CPEs. Okay. Now you think of a problem where you have multiple nodes all across a given area, and you need to form clusters of size L. So L could be optimal cluster size. Okay, so we want to make clusters of size L, exactly size L, or it could be a little bit greater than L, but we want majority of the clusters of size L. So this is again a very classical problem that people haven't looked into. So we searched the literature, and then we figured out that this problem has not been addressed till date. So we try to develop a clustering algorithm for our application here. So briefly, what we did is that we actually first at the start of the network, we need to figure out who is the cluster initiator. Depending on certain parameters, we figure out, okay, some CPs can figure out, okay, I will initiate the cluster. Then they can send out the invitation to the nearby CPEs to join the cluster. Each cluster has a utility, which is a function of the cluster size. So each CPE, while joining a particular cluster, will see, okay, whether my utility is being maximized or not, if I join that cluster. So the decision on the join and permit to join is with the cluster initiator. So once the invitation is sent and a reply is received, so the cluster initiator decides, okay, whether to permit a particular CPE to join the cluster or not. And this process keeps on going. And finally, we see that we form clusters of size L. And then we can start our communication. Okay, so we considered two scenarios. One was Bhutan, from Maharashtra. We took one use case from Maharashtra and one from Malawi, which is in South Africa. And we took those parameters and evaluated the performance of our architecture. And again, we could see that the energy efficiency of our system was pretty much good, while we were providing throughput which was close to what was there in the conventional architecture. And from the network setup perspective, because we did not require to establish these UHF nodes at each of these different villages, our network setup cost went down tremendously. So this actually meant that the service providers can spend very much less in capital expenditure to provide services to these in this fashion. Okay, so only you need to have a point of presence based stations, and then the other things are taken care of by the users themselves. The other thing is that if you look at the total network cost, we could see that if the population is sparse, our solution performs pretty better in terms of the total network cost as well. But if the population is dense in a village, then obviously the other solution is you can have a small base station in that village and then have a point-to-point connectivity to that village. So that's it from my side. Just the concluding remarks is that this was a small attempt that we made towards figuring out an energy efficient and low cost solution for rural broadband access. And we could see from this small attempt, we could get a lot of research problems that we are actually working on to solve. Now we want to go from theory to practice. So this was a theoretical part. We are actually working on implementing these systems. So we are developing low complexity distributed beamforming prototypes. We have finalized the algorithm. In fact, the prototype is also ready. We are in the process of filing a patent for that. Once this is done, then we can move forward to implementing a small cluster and then see its performance in practical scenarios. And if you see, this technology does not just limited to rural broadband, but it is also has a huge application scope in military applications, for example, where we need secure and low power communications. In network coded transmissions, where here we see that we are transmitting from one cluster to a base station, but we can also extend it to from cluster transmission to another cluster transmission and so on. So each node does not have a complete information. It has some partial information. So it also increase the security of communication as well as it can also improve in the reliability. So that's it from my side. Thank you very much. I'm happy to take up any questions if you have.
Thank you, Professor Satyam, for the enlightening talk. And we can take questions from the audience now.
So I had a question. So I just wanted to understand this distributed beamforming. So does it also depend on the phase may also depend on the distance of the CP to the base station, right? So does the CP need to be aware at what is its distance from the base station?
Yeah, thank you, Vishal. Yes, so the main objective that we are trying to address here is that we want all the signals to add up to be in phase at the receiver. Now these signals the phase can change with respect to if you have a change in the channel conditions, channel fading effects is there, it will change the phase. The distance also contributes to the phase. The small time difference between the two receiver will also contribute to the phase. The frequency drift between the two transmitters will also contribute to the phase. So yes, so this needs to be taken care of at every time instant while these CPs are transmitting to the base station, right? So one mechanism is we have a constant feedback that comes in from the base station. So what people suggested is that if you have a phase difference between say 30 degrees, then it is fine. You will get almost close to the optimal performance. But if the phase degrades beyond that, then we will have some degradation in performance. So the main effort is now we need to keep that phase in that particular boundary. So we can have a constant feedback from the base station, okay, how the signal is behaving, and then based on certain algorithms, we can adjust the phases at the individual transmitters.
Okay, so a base station will give feedback about each CP. What is the phase of each CP?
No, it cannot give for each CP because it cannot distinguish between the two signals coming from different CPs because these are being transmitted at the same frequency. So it cannot distinguish. It can give a combined signal saying whether I am getting a proper SNR or not. So if the proper SNR is not being received, it can send, let's say, a NAC, a negative acknowledgement. And then these CPs, what they can do is they can use some algorithms to kind of align their phases in a particular direction so that the phase is added up. So again, this is an iterative algorithm and it takes multiple iterations to converge.
Okay. Okay. Thank you.
Thank you.
So once again, we would like to thank Professor Satyam for the informative and engaging talk. And as discussed before, this is a reminder to the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details, and the links have already been pasted in the chat box. The link to the recorded video will be posted on the web page. So thank you everyone and have a great evening.
Thank you so much for having me.